Okay, picture this. You're standing in a completely pitch black room. The doors are perfectly sealed, the windows are shuttered tight, and there is absolutely zero light getting in. Just take a second to really imagine that kind of total, suffocating darkness. Now look around. Can you see the walls? Can you see your own hands right in front of your face? The answer, of course, is no. But why? Your eyes are wide open, your brain is fully functioning, yet everything around you is completely invisible. Well, this simple little thought experiment reveals the absolute most fundamental rule of human vision.
And that rule is this: we don't actually see objects, we see light. You see, light is a form of energy that's entirely responsible for our sense of sight. Without this energy either being emitted directly from an object or bouncing off that object and traveling directly into our eyes, that object is quite literally invisible to us. It's the interaction of light with the physical world that actually paints the picture we call reality.
Welcome to this explainer. I am absolutely thrilled you're here today because we are going to demystify some of the incredible optical illusions we experience every single day. We completely take our vision for granted, but the physics of how light travels, bounces, and tricks our brains is honestly nothing short of magical. So let's start making sense of the light around us.
Here's our roadmap for today. First, we'll uncover the secret to seeing. Second, the rules of reflection. Third, we'll compare mirrors to rough surfaces. Fourth, we'll look at the everyday magic of mirrors. And lastly, protecting your vision. Let's get right into it.
Part 1. The secret to seeing. Emitting versus bouncing light.
So we know we need light to see, but where does the light we rely on actually come from? Well, in our universe, stuff basically falls into two camps. First, you've got luminous objects. These are the powerhouses. They produce their own light energy. Think of the sun burning in space, the stars, or even just the light bulb glowing in your room. Then you have illuminated objects. These objects do not produce a single drop of their own light. They only become visible because they borrow light from luminous objects, reflecting it back to our eyes. Actually, the moon is a perfect example of this. It looks incredibly bright in the night sky, right? But it's really just a giant rocky illuminated object reflecting the sun's luminous energy. The table in front of you, the walls, the device you're watching this on, for the most part, we navigate a world entirely made up of illuminated objects.
Moving on to Part 2, the rules of reflection, the predictable bounce.
So, when that light finally hits an illuminated object, how exactly does it bounce? Well, it brilliantly follows the first law of reflection. Imagine a flashlight shooting a single ray of light across a flat piece of paper toward a mirror. When the light hits the mirror, it bounces off, traveling right along that exact same piece of paper. If you were to fold that paper down, the bouncing ray would just vanish. Why? Because the incoming light, the bouncing light, and the mirror's surface all interact on a single, flat, continuous plane. They never just twist off into some random 3D direction. They stay perfectly aligned on the same flat plane. To understand this a bit better, let's define the anatomy of this bounce. We use three crucial terms here. The incident ray is the incoming beam of light, the one actually falling onto the surface. The reflected ray is the beam that bounces back off the surface. And then we have the normal. Now, the normal isn't an actual beam of light. It's just an imaginary line drawn exactly perpendicular, or at a 90-degree angle, to the reflecting surface, right at the exact spot where the incident ray hits. The normal just gives us a perfect mathematical baseline to measure exactly what the light is doing.
Which brings us to this second law of reflection. And guys, this is a law of physics that never ever fails. The angle of incidence, which is the angle between the incoming ray and our imaginary normal line, is always equal to the angle of reflection. Always. If light strikes a flat mirror at a 30-degree angle to the normal, it will reliably bounce off at exactly a 30-degree angle, on the exact opposite side. If it hits at 45 degrees, boom, it leaves at 45 degrees. It is incredibly precise and totally predictable every single time.
Section 3. Mirrors versus rough surfaces. Why isn't a piece of paper a mirror?
So if light always reflects so perfectly predictably, why doesn't a flat piece of paper look like a mirror? Like, why can't you see your reflection in a cardboard box? Well, it all comes down to smooth versus rough. In what we call regular reflection, which happens on incredibly smooth surfaces. Think of a highly polished mirror or a perfectly calm lake. Parallel rays of light hit a flat surface. Because the surface is perfectly flat, all their imaginary normal lines point straight up. So the rays all bounce off completely parallel to each other, carrying a crisp, clear image straight to your eye. But then we have diffused reflection. This happens on rough surfaces. Now, a piece of paper or cardboard might feel smooth to your hand, but at a microscopic level, it's actually jagged and bumpy like a mountain range.
Now, it's absolutely critical to understand that diffused reflection does not mean the laws of physics are broken. The angle of incidence still perfectly equals the angle of reflection for every single microscopic ray of light. But because the surface is so bumpy, the imaginary normal lines are pointing in millions of different crazy directions. So when the parallel light rays hit those microscopic bumps, they scatter and bounce into wildly different directions. That scattering completely destroys the coherent image, which is exactly why a piece of paper looks illuminated but definitely doesn't reflect your face back at you.
All right, part 4, the magic of mirrors, illusions in everyday life.
Let's unpack some of the visual magic tricks regular plane mirrors play on our brains every single day. When you look into a standard flat plane mirror, the image you see has 4 distinct characteristics. First, it's virtual. The light rays aren't actually passing through the wall in front of you. Your brain is just being tricked into extending the reflected rays backward. Second, it's upright. You aren't upside down. Third, the reflection is the exact same size as you are. And finally, it's the same distance from the mirror. So the really wild part is that if you stand 1 meter away from a mirror, your virtual reflection is simulated perfectly as being exactly 1 meter inside the glass. To your brain, your clone is standing exactly 2 meters away from you.
But of course, there's a catch here: lateral inversion. Try this little experiment next time you're in the bathroom. Stand in front of the mirror and touch your left ear with your right hand. When you look at the image, your mirror clone is doing the exact opposite. They're touching their right ear with their left hand. Plane mirrors perfectly reverse left and right.
And things get really interesting when we start adding more mirrors into the mix. If you place multiple mirrors at angles to one another, the light doesn't just bounce once, it bounces back and forth between the reflecting surfaces. This is a super relatable experience if you've ever been to a barber shop. The barber holds a mirror behind you, the light from the back of your head hits that mirror, bounces over to the mirror in front of you, and then finally bounces right into your eyes. It's basically light playing a microscopic game of ping pong just so you can check out your new haircut.
We can even use these multiple reflections to make some pretty amazing art. A kaleidoscope is an ingenious little toy that uses 2 or 3 mirrors arranged in a tube, specifically placed at 60-degree angles to one another. Inside the tube are these small pieces of colored glass. Because of that 60-degree angle, the light bounces around inside the tube to create 5 perfectly symmetrical virtual images of those scattered glass pieces. When you turn the toy, the glass tumbles, and the multiple reflections create this endless, shifting loop of geometric beauty. It's so cool.
Finally, Section 5, protecting your vision, caring for the receiver.
We've spent this whole explainer talking about the fascinating ways light travels, bounces, and scatters, so we definitely need to wrap up by talking about caring for the delicate biological camera that actually catches all those bouncing rays, your eye. Your eyes are incredible instruments, but they require some strict care based on the science we just went over. First, always visit an eye specialist regularly to ensure your natural lenses are working properly. Second, avoid extreme lighting conditions. Don't strain your eyes in super dim light, and literally never look directly at intensely bright luminous objects like the sun. Third, if dust gets in your eye, wash it quickly with cold water. Never rub it, as you could actually scratch your cornea. And finally, try to maintain a distance of at least 25 centimeters between your eyes and the book or screen you're reading to prevent optical strain.
And speaking of safety, we really have to look at this crucial comparison. Safe ambient light, the kind naturally bouncing off the illuminated objects around your room, is scattered and easily processed by your pupil. But laser pointers? They are an entirely different story. A laser is a highly intense, highly concentrated, perfectly parallel beam of pure light energy. Because it doesn't scatter at all, if a laser beam hits your eye, that intense energy is focused entirely onto your retina. It can literally burn the cells right at the back of your eye, causing severe, permanent damage, and even blindness. So seriously, never, ever shine a laser pointer anywhere near a human eye.
Okay, to end on a slightly lighter note, check out this fascinating biology fact about how eyes process light. When you walk into a dimly lit room, your pupil actually physically expands, getting wider to act like a larger net, trying to catch as many of those scarce bouncing light rays as it possibly can. But human vision is honestly nothing compared to nocturnal animals. Nightbirds can survive in near absolute darkness because their retinas are uniquely designed. They have very few cones, which are what detect color, and a massive number of rods, which are specialized cells that detect even the faintest, tiniest traces of light. Their biology is just perfectly evolved for a world without the sun.
Which brings us to our final, provocative thought for this explainer. We know that mirrors placed at angles, like in our kaleidoscope, multiply the reflected light to create several images. But what do you think happens if you place a luminous object, like a lit candle, exactly between 2 perfectly parallel plane mirrors? Think about it. the light rays are bouncing perfectly straight back and forth, endlessly, between the two surfaces. So, how many reflections would that actually create? I highly encourage you to set up a couple of mirrors and test this out for yourself, because witnessing infinity right in your own bedroom is an experience you definitely won't forget. Thanks so much for joining me on this explainer, and keep looking